Well, how about them gators? Told you. I've been watching these guys for over 40 years. I get a pretty good idea when they're pretty good. They're pretty good. They might even be better than pretty good. We'll find out in 2 weeks. You know about this and this. Fair game stuff. What we get through today. I haven't even finished writing the quiz yet. No big deal to me. I like quizzes and exams to be concurrent with material. Question 1912. Imagine a water system buffered at pH 6.00. Imagine you're in the laboratory. You're dealing with an assignment 5 unknown sample, which is water soluble. You find out that it contains sodium ion by flame test. That means you're not going to succeed in testing successfully for calcium ion by flame analysis, because the sodium ion flame is dominant. So you are left with no recourse other than to test for calcium ion as a component of the sample by precipitation. The precipitation methods, which you learned about in assignment 3 in the laboratory, which we've talked about in class: calcium hydroxide, calcium sulfate, calcium carbonate. Forget calcium hydroxide. That is by far the most soluble of these three materials. And if you can precipitate calcium hydroxide, you've got a system which is obviously quite basic, which means you surely can precipitate calcium carbonate as well as calcium sulfate. Has it occurred to you that you can create conditions for which the solubility of calcium carbonate can be calculated strictly from its KSP, where you don't have to pay attention to KB carbonate ion? What are these conditions? We have had to consider KB carbonate ion in calculating solubility of calcium carbonate as a consequence of carbonate ion hydrolysis, right? Carbonate ion plus water, double arrows, bicarb ion, and hydroxide ion. How do you want to shut down that reaction? How do you want to stop carbonate from hydrolyzing appreciably?
You do it in basic solution. Very basic. Something strong.
Yeah. You jack up the hydroxide ion concentration. Now you got to be careful about this. There's a ticklish challenge problem regarding this at the end of chapter 19. We'll be there shortly. If you make the hydroxide ion concentration quite large, now you might co-precipitate calcium hydroxide. But you're going to stop the hydrolysis of carbonate ion nonetheless if you make the system sufficiently basic. But now we're talking about a system which is obviously acidic, mildly so, but nevertheless acidic, pH 6.00. So given that we've already looked at the solubility of calcium carbonate in straight water, where we get a pH 10.0, and water solution buffered at pH 8.0, we know that calcium carbonate is more soluble in this system than either of the systems so far considered. So you're in the lab. You make a solution of your sample. Sample's water soluble. Does it or does it not contain calcium ion? Well, if the sample does contain calcium ion, then when you dissolve the sample, calcium ion is now swimming around in the solution, if the sample's soluble. You observe solution pH. Because when you prepare a solution of an unknown with deionized water, The first test you are to make always is solution pH. Because you can make more decisions about ions which can, cannot, or still might be present based on that result. You get a pH of 6.0. You're at the side shelf. Shall I select sodium sulfate solution and try to precipitate calcium ion as calcium sulfate if the solution contains calcium ion? Or shall I select sodium carbonate solution and try to precipitate calcium ion as the carbonate? Well, with that question in mind, let's take a look at this question from an analytic standpoint. At pH 6.00, the first thing we want to realize is that the solubility of calcium sulfate may still be calculated correctly strictly from its KSP. Why? Because at this very mildly acidic system, sulfate ion still isn't going to hydrolyze to any extent at all that's meaningful. So I've written here, solubility of calcium sulfate is still the square root of KSP, which is this number. But how do we know this is correct? We have to be sure that sulfate ion plus water, establishing the equilibrium with hydrogen sulfate ion and hydroxide ion, is practically speaking a no-go process. A reaction which, as written, sulfate ion plus water, is going essentially no place. To get a handle on that, I'll use Kb sulfate. I could just as well use Ka hydrogen sulfate ion. It makes no difference. Because what I need to do, after recognizing from a material balance standpoint that the only possible other form of sulfate ion is hydrogen sulfate ion, correct? You're not going to tell me another form of sulfate ion is sulfuric acid molecule, are you? You're not getting any sulfuric acid molecules in water solution at measurable concentration. Remember sulfuric acid? Strong acid, ionization extent 100%. So H2SO4, quote unquote, is not a viable form of sulfate ion in water solution. So any equilibrium which connects the concentrations of sulfate ion and hydrogen sulfate ion will allow me to answer this question. To what extent does sulfate ion hydrolyze? So with Kb sulfate, here's the equilibrium constant expression. I'll rearrange it to get a concentration ratio of sulfate ion molarity to hydrogen sulfate ion molarity. I put in the corresponding values for hydroxide ion concentration in Kb. That's 12,000 to 1. That's good enough for me. For every one hydrogen sulfate ion swimming around in there, I got 12,000 of these sulfate ions. Who cares about hydrogen sulfate ion?
Right. I thought you were trying to avoid using Kb.
Huh? I didn't say that. I said we want to use any equilibrium which allow us to interconnect the molarity of sulfate ion and hydrogen sulfate ion. Consequently, we use Kb, which I did, or Ka hydrogen sulfate ion. Either one works.
In this second equation, why did you ignore the hydroxide when you took the reciprocal?
I didn't ignore hydroxide. Here it is. That's hydroxide molarity. Now, how about calcium carbonate at pH 6? We know it's more soluble than for the pH 8 and pH 10 systems that we've so far analyzed. So I'll revisit this equilibrium reaction. Because it involves calcium carbonate reacting with water, it accounts for carbonate ion hydrolysis, gives me a handle on pH, gives me a handle on solubility, and gives me a handle on the possible viable forms of carbonate containing things in the pot. What are the possible viable forms of carbonate containing things in the pot? Bicarb ion, which we've got in this expression, or carbonate ion, or quote unquote H2CO3. Now, if you recall the analysis of this very same system, but at pH 8, which we've already done, we found a bicarb concentration to carbonate concentration ratio of 210 to 1. 210 to 1. That was at pH 8. Now we got a system that's 100 times more acidic. What happens to this 210 to 1 ratio? What does it become? 210 to 1 is bicarb to carbonate. That's at pH 8. Bicarb to carbonate. And we know as we make the system more acidic, carbonate becomes ever so more effectively killed, murdered, destroyed, wiped out, eliminated. So what happens to this 210 to 1 ratio when I change the pH to 6? Instead of 210 to 1, what is it now? 21,000 to 1. You write the equilibrium analysis if you need to. It's all in the notes. But all these concentration ratios to which we are referring, since the species we are considering are all having an existence which depends on pH. Once you know pH, you can figure out what you got in the pot and what you ain't got in the pot if they are species whose livelihoods depend on pH. So, we got this. We know the calcium ion in the system doesn't do anything, so that will be the solubility. If we can calculate calcium ion molarity, we got the solubility of calcium carbonate. We know the hydroxide ion molarity because this system is fixed at pH 6.00. What we don't know is the bicarb molarity. We found out at pH 8 that the calcium ion molarity and the bicarb molarity were practically the same. So we call them each S. But that's not going to be true at pH 6. Do you remember in your mind's eye what concentration ratio we got for bicarb to quote-unquote H2CO3 at pH 8? Since we did the analysis, since it's in the notes, I'm curious if you remember this. Bicarb molarity over H2CO3 molarity, with quotes on H2CO3, at pH 8. 42 to 1. Those are the numbers. What happens to that ratio when we go to pH 6? Is it still 42 to 1? What is it now? It's 0.42 to 1. When we get to pH 6, the dominant carbonate-containing stuff in the pot is no longer bicarb ion. It's now quote-unquote H2CO3. In any case, regarding the negligibility of carbonate ion, I wrote that here. And here's the analysis with respect to bicarb versus quote-unquote H2CO3. I'm using Kb bicarb. I don't have to. I could use Ka for quote-unquote H2CO3. Because that equilibrium, KaH2CO3, like this one, is also an equilibrium which interrelates the molarities of bicarb to quote-unquote H2CO3 as a function of pH. That's what we need. So with this, I'm going straight to a molarity ratio of H2CO3 to bicarb as opposed to HCO3 minus to H2CO3, which we just talked about. Well, it's 2.4 to 1. For every one of these, you got 2.4 of these. This is the dominant stuff. So how do we figure that into this equilibrium constant expression? How do we use this information to get a handle on the value of question mark, on the value of question mark in terms of S? So we can write one equation with one unknown, that unknown being S. I go back to this. I've already recognized at this pH, if I put in here carbonate plus this, all the possible forms of carbonate-containing stuff, this is out. It's too acidic. That's why I didn't even write it here. So, this has told me the molarity of this is 2.4 times the molarity of this. So I'll put that in here. Take this out, put in 2.4 times the molarity of bicarb. So S is 3.4 molarity bicarb. So bicarb in terms of S is this. Done. I'll put it in my K expression. One equation, one unknown, solve it, and I got 2.1 times 10 to the minus 2 molar. Which, if you go back through what we've already done, you will see this solubility exceeds the solubility as it must for calcium carbonate at pH 8. pH 8, I think we got 3.0 times 10 to the minus 3 or something like that. Now then, you see this solubility? 2.1 times 10 to the minus 2. You see the solubility up there for calcium sulfate? 3.0 times 10 to the minus 3. If the system remains at pH 6 for this analysis, if the system remains at pH 6, which material is easier to form? Calcium sulfate or calcium carbonate?
Calcium sulfate.
Calcium sulfate, it has a lower solubility. That makes it more stable and less soluble. Now let's go back to the laboratory. The purpose of which is to keep you on your toes. The only complaint of consequence I ever get about 46 laboratory is that from students who say, I don't have enough time to do the unknowns. And my response to that is simple, like hell you don't. Because if you understand what's going on, I've given you twice as much time at least that you need. And if you don't know what's going on, I can give you all week. You'll be in there blindly doing every test, test after test after test after test, without thinking. That's no way to operate. Go back to the laboratory. You got your sample. It's got sodium ion in it, which flame test has told you. You make the solution, sample soluble, you got a pH of 6.0. You're standing at the side shelf. You want to test this thing for calcium ion, the solution you're looking at. Before you see half molar sodium sulfate solution and half molar sodium carbonate solution, because those are the respective sulfate carbonate solutions you have available for use in the laboratory. Which one are you going to grab? You're going to grab the sodium sulfate solution and put in the sulfate ion? Or are you going to grab the carbonate solution and put in the carbonate ion? Which one are you going to grab?
Sodium sulfate.
How many are you going to grab sodium sulfate? I'm grabbing sodium carbonate. Because sodium carbonate is easier to form. Because you think this solution you made in the laboratory is a buffer? You think it's got a pH fixed at 6.0? You know what's going to happen when you start putting carbonate in there? The pH is going blink! And here comes calcium carbonate, much easier to form than calcium sulfate. You see, you got to think. There's a dirty, rotten question I asked you, isn't it? Like hell it is. It's saying, are you aware of the environment that you're in when you're in that laboratory? Are you thinking? Because once you turn off the thinking, life is murderous and miserable. I'm serious about that. I don't care what you try to do. You've heard this sermon a million times. You'll probably hear it a million times more. Because even though it is highly likely that few of you will do much with the specific chemistry that we've talked about in this gathering, if you're going to do anything of consequence, anything of significance, anything of importance in this life, it's going to involve sharp, clear, logical, analytical analysis. And by damn, this course is about that too. So if we can sharpen up your ability to analyze a problem, we're doing you a big service. And I'm convinced that is exactly the case, because of the number of students who have been with me, and on occasion, as I've already told you, hated my guts while they were in here. Because for the first time in their life they had to work. Isn't that too damn bad? I mean, you think life is so easy that everything's going to be given to you? That's why I said to you. Not just you, but any student I come across. If I run this university, I'm going to be the registrar. You come to me, you want to get in. Are you here for a degree, or are you here for an education? Everybody says degree, forget it. You ain't getting in no way, no how. But if you're here for the education, in you go. Because if you get the education, you get the degree. But I know a lot of people with degrees who don't know squat because they never got an education. And I don't want any part of that kind of person. How about that for an attitude? You already know it. On we go. Yes?
That line that says S equals C into plus equals HCO3 plus HCO3 plus equals 2.4 HCO.
Yeah.
Well, anyway, that line.
What about it?
Is that material balance?
It's material balance for carbonate-containing things, sure.
Okay.
Absolutely. So, bear in mind that if you did grab the sulfate ion solution, you'd still win. But if you were careful, because by now I expect you are in assignment 3, if not past it, in preparing calcium sulfate in the laboratory, as opposed to preparing calcium carbonate, did you find in the laboratory, because you did this stuff, did your observations tell you that when you could put together calcium ion and carbonate, where? Calcium carbonate just boom, drops right out. But when you put together calcium ion and sulfate ion, or a source of sulfate ion, because in the laboratory, you didn't use sulfate ion to react with calcium ion to make calcium sulfate, you use hydrogen sulfate ion. You mixed up calcium ion with 3 molar sulfuric acid solution. And eventually you got nice, well-developed crystals. Nice, well-developed crystals because the precipitation of calcium sulfate is not immediate. Requires a little bit of time. And one of the headaches that students cause for themselves in laboratory doing unknown analysis is, in a case like this, calcium ion's in the solution, add sulfate, no precipitated immediately. No calcium ion, way to go. 15 seconds later, there's the calcium sulfate. But they were in a hurry. In a hurry because they were not thinking. And so they said calcium ion's not in the system. And on occasion, these people have come to see me. What'd you do? They just told me I just described what they did. I said, too bad. You didn't make the observations that you were supposed to have made when you in fact made this precipitate yourself in the laboratory. Hey, you think science depends on observations? We don't even need to talk about that, do we? Now then, we go to the last general topic for chapter 19, for which we really already engaged in certain considerations, and certain variations. Changing the solubility of a salt which is slightly soluble in water by chemical methods. We've been doing that with these pH considerations for calcium carbonate. Now we're going to look at it in somewhat more of a general fashion. Point. What we're going to do now, because what we didn't hear was really to pay attention to any specific chemistry involving calcium carbonate reacting with the stuff that changed the pH. Now we're going to do that. For example, calcium carbonate dissolved in water versus calcium carbonate dissolved in ammonium chloride solution. In which of these systems, water or ammonium chloride solution, is calcium carbonate guaranteed to be more soluble? Ammonium chloride solution. Why? Because Ammonium ion is a stronger acid than water. And ammonium ion, as well as chloride ion, are not precipitators of calcium ion. So if I mix up calcium carbonate with ammonium chloride solution, I'm guaranteed to dissolve it more effectively relative to dissolving calcium carbonate in water. So with that, we're going to pay attention to the specific chemistry of the system. Ammonium ion reacting with calcium carbonate, we'll take it from there. But before we do that, I need to call your attention to the statement which you see at the top of page 1913 in the notes, written in bold, starting with important statement. You look at the important statement. The important statement tells you, if I take a salt of limited solubility in water, and the anion component of this salt is a base that's stronger than water, I am guaranteed to increase the solubility of that salt by treating a mixture of water with that salt with any acid that's stronger than water, provided that this acid is not a precipitator of calcium ion. Or I mean, not calcium ion, but of the salt in question. Provided that the acid solution is not a precipitator of the salt in question. So with that, we realize what we've already just recognized, and that is calcium carbonate is more soluble in ammonium chloride solution than it is in straight water. Because neither ammonium ion or chloride ion foster precipitation of calcium ion in any form, or calcium carbonate. And since ammonium ion is a better acid than water, you're guaranteed to destroy carbonate ion more effectively in the ammonium chloride solution. But how about dissolving calcium sulfate in this solution? Is this solution fairly acidic? Ha ha! The pH of this solution is 1.0. Got a hydronium ion concentration of 10th molar. That's pretty acidic, don't you think? Now we know, if you want to get sulfate ion to hydrolyze, since sulfate ion is such a feeble, weak base, you better hammer it with a pretty high hydronium ion concentration. This has a pretty high hydronium ion concentration, the sodium hydrogen sulfate solution. However, it also has a source of sulfate ion. Hydrogen sulfate ion is a precipitator of calcium sulfate. You believe me? Didn't we just remind you a moment ago about how you made calcium sulfate in the laboratory? You mixed up calcium chloride solution with 3 molar sulfuric acid. Is 3 molar sulfuric acid pretty acidic? You're damn tootin'. Yet that system effectively precipitates calcium sulfate. So it must be that the attack of hydronium ion and sulfate ion is not nearly a significant thermodynamic factor as is the tendency of calcium ion to react with hydrogen sulfate ion and make calcium sulfate. More on this thermodynamic factors in greater detail when we get to chapter 20 and 21. But everything we have so far done this term is all thermodynamics. We have done nothing but thermodynamics. So regarding the solubility of calcium sulfate in my sodium hydrogen sulfate solution, you got to get a Ka hydrogen sulfate ion, consider Ka hydrogen sulfate ion to resolve this issue. So I've written the Ka expression, and the hydrogen sulfate ion, sodium hydrogen sulfate solution all by itself, we have x squared over 1.0 minus x, because the m sub I value is 1.0. And we get a hydronium ion concentration of 0.10, pH 1.0, just like we told you, as well as a sulfate ion concentration of 0.10. So, We go to our calcium sulfate equilibrium reaction. The equilibrium reaction for which the K value is KSP. Recognize that the concentration of calcium ion will be the solubility. And in this solution, the sulfate ion concentration will be S, what you get from this reaction, plus what you got from the sodium hydrogen sulfate solution. Well, I'll put this in KSP and I'll solve it. I get 9.1 times 10 to the minus 5 molar. Isn't this number a good deal smaller than that number? There's the solubility of calcium sulfate in straight water. 3.0 times 10 to the minus 3. This is a lot smaller, which means the calcium sulfate is a lot less soluble in the sodium hydrogen sulfate solution. So again, the statement in bold. You will certainly increase the solubility of a salt of limited solubility in water if it's composed of an anion which is subject to acid attack, provided that the acid you use is not a precipitator of that material. In laboratory, for example, for further example, when you get to assignment 7, you will at that time do some chemistry in which you will prepare silver sulfide and zinc sulfide and copper sulfide. The sulfide ion is a strong base? You know that. Damn strong base. So do you think it's reasonable as a first attempt to try to dissolve a sulfide by hitting it with hydronium ion? Of course. But with silver sulfide and copper sulfide, you won't get any place. The solubility is still so slight, practically speaking, not soluble. So, if you take the acid H2S and try to use that to assist in dissolving a semi-soluble sulfide, forget it. You will assist in precipitating the semi-soluble sulfide, not dissolving it. So let's now tackle the issue that we said we were going to tackle.
I have a question for your calculation up there. You assume that the dissolving of calcium sulfate doesn't affect the ionization of the hydrogen sulfate ion. Like, wouldn't the solubility lie somewhere between the two? Like, doesn't that reaction have an effect on the?
Do you really think that 9.1 times 10 to the minus 5 moles per liter of sulfate ion, which is what you put in the system by establishing this equilibrium, you think that's going to have an impact on hydrogen sulfide ion's ability to ionize? Not. You do the arithmetic for yourself, prove it. It's too small. So we go to this. Solubility of calcium carbonate, 1 molar ammonium chloride solution. Statement. Number 1, for any system, PSI. Calcium carbonate. Component ions, calcium ion and carbonate ion, as we well know. Ammonium ion, chloride ion, water. That stuff by now should be old hat to you. Next consideration. What is it? After we got our PSI, what do we do now? What have we done previously after we have constructed PSIs? We wrote reaction equation, didn't we? Well, let's do it again. And indeed, our strongest base in this system is carbonate ion, which is part and parcel of calcium carbonate. Strong acid ammonium ion. when ammonium ion attacks calcium carbonate, as our acid-base chemistry tells us, after putting calcium ion in solution, we get bicarb ion and ammonia. Is the reaction of ammonium ion carbonate ion, not this reaction, ammonium ion carbonate ion, products, bicarb ion and ammonia, is that a large extent or small extent reaction?
Large extent.
If you look at the acid-base table, large extent. Which of course keeps with our recognition that ammonium ion attacks carbonate ion a hell of a lot more effectively than water, because ammonium ion is a better acid. Ammonium ion is not a strong acid at all, but it's a whole lot stronger than water. All right? Now we want the K expression. I'll condense the formula for bicarb ion just to expedite matters. There's my K. What's the K value? Well, I don't know. This is a complex equilibrium. Now, of course, it's in the notes. But when I wrote the notes, and I wanted to get this K value, what did I do? You've already been through this. Now let's go through it again. You think you might have to do something like this on tomorrow's quiz? You're damn right. You better believe it, absolutely and for sure. I let this reaction equation, this equilibrium reaction equation, I let it talk to me. That's the way I know what K's this thing is composed of. All right, it's talking to me. The first thing it says is that a component K of this has got to be KSP calcium carbonate, because this thing contains calcium carbonate. So, without any further ado, to be poetic about this, I'll multiply what I got, carbonate ion top and bottom, because calcium ion molarity times carbonate ion molarity is KSP calcium carbonate. And then I say, equilibrium reaction. What else has we got to tell me? What other K's am I looking for? And I look at it and say, aha, ammonium ion on the left, ammonia on the right. What equilibrium, in my mind's eye, connects the molarities of ammonium ion and ammonia? How about Ka ammonium ion? Or Kb ammonia? Who gives a damn? Either one works. Well then, oh, yeah, we know you're here, but you're in the way. Well, get out of there. I'll put it back when we need it. I want to go for Ka ammonium ion. I don't have to, but that'll do me. And now, here's ammonium ion, check. Ammonia, hydronium ion. There's Ka ammonium ion. So now I got KSP calcium carbonate times Ka ammonium ion. Well, what else have I got in this pot? Well, I got carbonate ion as a component of this stuff, and bicarb on the right. So in my mind's eye, what equilibrium with which I'm familiar interconnects the molarities of carbonate and bicarb? And these are all acid-base reactions, so they always got to have hydronium ion or hydroxide ion in them, because they all involve H plus exchange. See how this thing is talking to me? It's got to talk to you too. Well, let's see what I got here. Bicarb here, carbonate here, hydronium ion here. Tell me, am I familiar with a reaction where bicarb is on one side of the reaction arrow, or double arrows, and hydronium ion and carbonate ions on the other side? What is this? Is it Ka bicarb? Or in this case, is it 1 over Ka bicarb? What is it? 1 over, right? So, here we are. Check, check, check. And here it is. KSP calcium carbonate. Ka ammonium ion. Ka bicarb. Did I have to use Ka ammonium ion? No. I could have operated with Kb ammonia. Did I have to use Ka bicarb? No. I could have operated with Kb carbonate. Doesn't make any difference. I was going to get the same answer. And now you just put in the numbers. 6.2 times 10 to the minus 9. 5.6 times 10 to the minus 10. 4.8 times 10 to the minus 11. I told you I got the table in my head. So what? No big deal. If you do this for year after year after year after year, you'll have the table in your head as well. This equals 7.2 times 10 to the minus 8. I better check that because I'm doing this from memory. Yeah. And now we've evaluated K and are in position to tackle the solubility of calcium carbonate in ammonium chloride solution. From this point, we shall proceed next time.